Hey, AP Chemsters, this is Mrs. Vanderlei bringing you another edition of the Blank Wall series. Today, we did not quite get done with our discussion of ideal versus real gases. We talked about the premise of it and what makes a gas more real and less ideal. And if you recall, we have two factors that will alter this behavior. And the first one, and maybe the more important one, is if you adjust the pressure. If you shrink the volume, you increase pressure. If you just increase the pressure on it by squeezing on it or something, you are going to change the behavior of these gases, making them less ideal. Why is that? Do you remember? If these molecules are going to be closer together, then they have higher chances of collision, and higher collision would mean more attraction, the more opportunity for attraction. So like I made the analogy, if you're all squeezed together in the room, you're going to be very close to those molecules next to you, and that opportunity can have for the attraction. In the real world of atoms, our discussion led to, well, why does this proximity lead to greater attraction? And that's when the electrons will repel each other, the outer electrons of the two different atoms, leaving one, like a set of electrons are being moved away, allowing for the attraction of, let's say, atom 2 to the nucleus of atom 1. We call that polarizability. So that's why greater pressure leads to more attraction. The other one was if you slow down the molecule, so you decrease the temperature. Therefore, they have, again, a greater chance of attraction. Instead of going zoom, 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 zoom so fast, they have a chance to really have that, the electrons in the nucleus have that attraction. If you slow it down, then that attraction increases. So if you want to talk about in problem number 38, why gases behave less ideally, think more attraction. So why will gases behave at higher pressures? I think I just said that. So if you have higher pressure, what's going to happen? Well, let's see here. As pressure, what's happening, goes up, volume goes down. What's going on? So they're going to get closer together, and then you're going to have higher attraction. Sorry about that, because they are closer together. So more attraction means less ideal. So why do gases behave ideally at low pressures? That means if they're going to be more ideal, you have less attraction. So let's think about this. If you have low pressures, what did we say was going to happen with the volume? Well, if pressure goes down, what will volume do? Go up. Try to make a down arrow here. And volume goes up. So you have more space, therefore you have fewer collisions. And with fewer collisions, that means you have less opportunity for this attraction, therefore it's more ideal. Okay, it says now, which would you expect to behave less ideally? So less ideally. Why do gases behave less ideally? Because, there is more attraction. So we want to explain both of these in terms of why would one molecule over the other one have greater attraction. Well, we said today in class that water is a very special molecule. And if you are looking at in this case, a molecule and an atom, and they're fairly equal in molar mass. So what's going to make one thing different than another? It's not their mass, all right, it's their polarity. So water is a polar molecule. And do you remember what we said earlier? If you have a polar molecule, you have those partial charges. So you have, let's say, those partial positive and partial negative. So here, I'll even write that here. This is going to be a partial negative, and that's your partial positive. And those partial charges can then attract to the other partial charges of another water molecule. So there is actually great attraction between water, one water molecule and the next. What were the other ones? Well, you want to think of HF, because F is the most electronegative element. HCl and NH3. Those have the four greatest electronegative elements, and they're going to be the most polar molecules, so they're going to have the most attraction. Now look at problem B. We're talking about helium versus xenon. They're both atomic. One is not going to be more polar than the other. They don't have the very electronegative elements involved here. They're just noble gases. So is there a difference between the two? And the answer is, well, yes. Okay, so think about kind of our demo today when we had um, Nick and Cassie going through the pinhole, or Saeed, and I'm trying to remember who else it was. Saeed and somebody. Was it Kayla? Anyway, trying to go through oh, it was Carly. How could I forget? Sorry, Carly, if you're listening. So Carly and Saeed going through the pinhole. Who's going to have an easier time going through the pinhole? That would be Carly. She had lower mass. Saeed is a bulky guy there, so it's going to take him a little extra effort. He's going to have to slow down perhaps to get through it. So size does matter here. And it also works with this idea of attraction. We didn't really talk about this necessarily, but go with this. Xenon is, I'm going to leave it down here, is a larger molecule. So it has more mass. If it has more mass, it has more electrons. If it has more electrons, there's greater polarizability. And what does that mean? It's going to have greater attraction between the outer electrons and the nucleus of the other xenon molecule. So you need more than one molecule here to talk about. And so that would be our answer for letter B. Pick the larger mass one. It's going to have more attraction. And as I tell my husband there, I've gained some weight since we've been married. I just tell him that, honey, there's just more of me to love. All right, so you have higher attraction. So, having said that, we don't need to do problem number 41, although it's a fantastic problem because it has my favorite equation here, the van der Waals equation, but oh well, that'll be another time. You do not need the math problem. You don't need it on the test, so don't panic, but you might have to explain these type of situations here, okay? I hope that helps. Take care, and we'll see you later.